Okay, in this section we'll be looking at symmetry and coordinate graphs. Specifically, we'll be looking at even and odd functions. So, odd functions are functions that have origin symmetry. I think origin symmetry is a little bit difficult to think about because the origin, of course, is the point 0, 0, and it's a little difficult to think about symmetry about a point rather than a line. So the coordinates can really help us out here. When a function has symmetry with respect to the origin, if point x, y is part of the graph, then the point negative x, negative y is part of the graph also. For example, this graph here is the cubic function y equals x to the third. So we know the point 2, 8 lies on this graph. 2 cubed equals 8. So 2, 8 lies on this graph. So according to this definition, that means that negative 2, negative 8 should also lie on this graph if it is in fact an odd function. And if you look at the graph here, negative 2, negative 8 right here, we see that point is in fact on the graph. This is an example of an odd function. Now, we're going to be very concerned with being able to tell just from the equation whether or not something is even or odd. So there's a test that we can perform for that. And the test is that we will find f of negative x. That means we'll plug in negative x for all of the x's. And if it is an odd function, our result should be the opposite of f of x. And we'll look at a few examples here in a minute. A couple other things to remember about odd functions. Functions with origin symmetry are, of course, called odd functions here. That was kind of redundant. And then functions with origin symmetry also have 180-degree rotational symmetry. So you'll see here in this picture that if I take this graph, if I rotate it 180 degrees in either direction, that the graph looks the same. So origin symmetry is really the same as 180 degree rotational symmetry, which is a little easier to picture. So let's look at some equations. Here we have f of x equals x to the third minus 2x. And our test that we use is f of negative x has to equal negative f of x, or the opposite of f of x. So if we plug in negative x for all of our x's here, we're going to see if this gives us the opposite of what we started with, or the same, or possibly neither one. So what we're going to see here is that whenever we have our negative x, when it's raised to the third power, that is going to retain the negative. For example, if I have negative 2 to the third power, that's negative 2 times negative 2 times negative 2. So that would be 4 times negative 2. That would give me negative 8. When you have an odd power, you're going to retain that negative. So this is going to be negative x to the third. For the negative 2x, we have negative 2 times negative x. Negative times negative here gives us a positive, so we'll have a positive 2x. Notice that doesn't have a power, but whenever we don't have a power for our variables, there's an invisible 1 there. So again, we have an odd power. So when we have those odd powers, the coefficients of those parts of the function change signs, giving us the opposite of what we started with. If we wanted to here, we could factor out a negative 1, which would leave us with x to the third minus 2x. And notice here that x to the third minus 2x is f of x. So what we have found here is that this equals negative f of x. So this is in fact an odd function. It has symmetry with respect to the origin. So let's do another example. For number 2, we have x to the 23rd minus 5x to the 5th plus 7x. So if we plug in negative x here. We're going to have negative x to the 23rd minus negative x to the 5th plus 7 times negative x. So what happens here, we have negative x to the 23rd. 23 is an odd number, so that means we're going to have negative x to the 23rd. We're going to subtract. Here we've got negative x to the 5th power, so that's going to give us negative x to the 5th. It's odd, so it keeps that negative. And then we've got 7 times negative x will give us negative 7x. Now right here we have two negatives together, and a negative times a negative gives us a positive. So we end up with negative x to the 23rd plus x to the 5th minus 7x. So we see here that everything is the opposite. We had a positive x to the 23rd, now we have a negative. We had a negative x to the 5th, now we have a positive. We had a positive x to the 7th, now we have a negative x to the 7th. So everything has changed signs. We could also think of it like this. If we factored out a negative 1, we would have x to the 23rd minus x to the 5th plus x to the 7th. We would notice here that this matches this, so we have the opposite of f of x that we started with. So this function here, number 2, is also odd. Now, whenever we look at number 3, things are a little bit different here. Whenever we have fractions, things are going to work a little bit differently. So I have 8x over x squared minus 3. So if I replace that x with a negative x, here, this would be my f of negative x, then I will see here that I will end up with a negative 8x over, when I have x squared here, whenever I square something, like negative 2 times negative 2, it gives me a positive 4. So if I have an even power, the negative just kind of disappears. I've got a positive x squared minus 3. Now, at first glance, you're going to think this does not have origin symmetry because we have this top number changed, but the bottom did not. However, we can write that negative out front, and then we'll have 8x over x squared minus 3. And we will notice here that 8x squared minus 8x over x squared minus 3 matches 8x over x squared minus 3. So this is negative f of x. This function is also odd. What we see when we have fractions is that if the numerator or denominator changes, then it is going to make that negative, that function negative. So, fractions are a little different. Number 4, if we look over here, if I do f of negative x, we get 1 over negative x squared plus 1. So I will end up with 1 over this even exponent here, just kind of erases that negative because negative times negative gives us a positive, plus 1. So what I see here is that what I started with, 1 over x squared plus 1, what I started with, 1 over x squared plus 1, is the same as what I ended with. I don't have any opposite signs here. So this one is not odd. Okay? Let's also talk about even functions. So let me adjust the view back here. Even functions have what we call y-axis reflective symmetry. We've worked with it a lot. It's a lot easier to picture. But for our coordinates, when a relation is symmetric about the y-axis, if xy is part of the graph, then we will have negative xy also as part of the graph. For example, in this graph here, we have the point 1, 4 that is on the graph. If we look over here, we also have negative 1 4. Both are part of the graph. Whenever we're looking for even functions, our test is that f of negative x is going to equal f of x, not the opposite of f of x, but exactly f of x, what we started with. Functions with y-axis symmetry, of course, are also called even functions, as you see in the title of this page. So let's try a few of these. The test is the same. We are still plugging in negative x, f of negative x. But our result that we're looking for is different. We want to get f of x here, the same thing that we started with. So, if we look at number 5, if I have f of negative x equals negative x to the 6th minus 5 times negative x squared, when I have even exponents, that just sort of erases that negative, because when I multiply something to an even power, then the negative is going to disappear. So I've got x to the 6th minus 5, and then this x squared, that negative there, is also going to go away. So what we see here is that our original matches our final, and that means that this is an even function. If we look at number 6, f of negative x is going to be 8 times negative x to the 4th plus negative x squared minus 5. So we will have 8x to the 4th. The sign, the negative is sort of erased there. We'll have x squared, and the 5 does not change at all because it does not have an x with it. So again, we see that we have f of x, and we end up also with f of x here. So we have another even function. Now, fractions are going to be different. Whenever we have f of negative x for number 7, we're going to have negative x to the 3rd over 5 times negative x minus negative x to the 7th. So in this case, let me adjust the screen here. So whenever we have this case, we're going to have negative x to the 3rd over negative 5x. And here, we're going to have a negative times a negative, so we'll get a positive x to the 7th. Now, at first glance, this appears that it is an odd function because everything changed signs. Our x to the 3rd changed signs, our 5x changed signs, and our x to the 7th changed signs. However, because this is a fraction, what we're dealing with here is we have a negative in the numerator. We also have a negative in the denominator. If I factored out a negative here, I would be left with 5x minus x to the 7th here. And whenever we have a negative on top and bottom, those two negatives are going to cancel each other out. That leaves us with x to the 3rd over 5x minus x to the 7th. So in this case, because the numerator was opposite and the denominator was opposite, a negative over a negative gives us a positive here. What we started with matches what we ended with. So this is also an even function. Okay. Our last example on this page here, we have 8 minus x squared over x to the 4th. So we will have 8 minus negative x squared over negative x to the 4th. So we will be given 8 minus x squared over x to the 4th. So we see that what we started with matches what we ended with. So this one is even. Now, that kind of seemed to be sort of a long process, but these are actually very quick problems. So I'm going to show you with a few more examples how these can be pretty simple. So for problems where we have a polynomial, that means there's no fractions, we just have different x's raised to different powers. So when we have polynomials like we see on this page, if we have an even function, then everything has an even exponent. So I have 3x squared minus 6. Now, 6 does not have an x with it, but I could put an x to the 0 here since there's 0 x's. Those are both even exponents. 2 and 0 are both even. If I were to plug in a negative here, they would not change signs because of those even exponents. So, this will be an even function. Number 10, I have an odd exponent here, and I have an even exponent here. So if I have both an odd and an even exponent in a problem, in a polynomial problem, then I know immediately it can be neither even nor odd. So this one, I would say, is neither. If we look at number 11, it initially looks like it might be an odd function. We've got 9x to the third, odd power, minus 7x. That doesn't have an exponent, but we could put a 1 there with it, which is an odd power. But we have this coefficient on the end. And remember I said a coefficient doesn't have an x, but we could put an x to the 0. 0 is an even number here. So in this case, number 11 is neither odd nor even. The last example we have here is number 12. We have 8x to the 5th plus 3x, even though it's not written there, to the first power. 5 and 1 are both odd powers, so I know that this will be an odd function. Okay? So when you have polynomials, you can just look at the exponents in your problem and decide pretty quickly whether or not those problems are even or odd or neither. Remember in our problems that we did earlier that fractions were a little more difficult. The key to fractions is that we've got to remember a positive over a positive, of course, gives us a positive. A positive over a negative would give us a negative. A negative over a positive would give us a negative. And a negative over a negative would give us a positive. Those are just our division rules. So whenever we look at problems like number 13, the numerator is just a 3. It's going to stay the same. It's going to be positive. The denominator, we're going to have x to the third and then x to the first, which makes this odd. It's going to change signs, which is going to be a negative. So positive over a negative is going to be a negative f of x, which means this is an odd function. Okay. For number 14, we've got 4x to the 5th that has an odd coefficient, so the numerator is going to change signs. In the denominator, we have x to the third, and over here x to the first power. Those are both odd, so that is going to change signs whenever we plug in a negative x. So in this case, a negative over a negative gives us a positive, which means that this is going to equal positive f of x, which makes it an even function. So you're going to look at the numerator and denominator separately, and then if you have a negative over a negative, it actually becomes a positive. The last two that we look at here, for number 15, we've got 3 minus x. Now, 3 is a coefficient. It doesn't have it written there, but it's like it's got an x to the 0 power. X has a coefficient of 1. So what we have here in the numerators, we have a odd exponent and an even exponent together, which means that the numerator here is neither. Now the denominator would be negative, but if we have one that's neither in the numerator or denominator, then our answer for this is that the function is neither odd nor even. So if you get neither on top or bottom, then the answer is neither. For number 16, we have 2x squared, even exponent, which is going to give us a positive in the numerator. We have x to the 4th minus 6, and there's no x here, but if there was, it would be x to the 0, so both of those exponents are even. So that is also going to give us a positive. So positive over positive, of course, is positive, so this is an even function that we're looking at